Hello, everyone. Welcome back. This is section 7.2, trigonometric manipulation. I wanted to show you some of the things that you need before we start this session. I have a list of formulas, and this includes all the first derivatives of our trigonometric functions. You need to know these pretty well, especially for this section. Also, these trig identities here, the 1 plus tangent squared x, the secant squared x, that's important as well. You also need to know, of course, sine squared x plus cosine squared x equals 1, and we will use that one quite a bit today. I want to point out at these top two on the right here, it says 1 plus tangent squared x equals secant squared x. Understand that I can rewrite that as tangent squared x equals secant squared x minus 1, or cotangent squared x equals cosecant squared x minus 1 if I need to. The other two that are not here that we really need are down here at the bottom of the screen in the middle, the red. It says sine squared x equals 1/2 1 minus cosine 2x, and cosine squared x equals 1/2 1 plus cosine 2x. The reason that we need these, in all what we're doing today, it's all about manipulating the trigonometry to get it into a form so that we can integrate it. If you recall from your trigonometry class, when you were learning all of this, they would give you problems like verify that the left side equals the right side and so on. We're going to be doing a lot of that today, and in some cases we're going to have to get a little creative with some of the things that we've already learned. So you'll need to know these derivatives and these Pythagorean rules, as well as these half angle down here at the bottom, the sine squared x and the cosine squared x. With that said, I want to show you the first theme of what it is that we're going to be doing. And I'm going to start with this example here. And I'm hoping that you recognize that this is a simple substitution. And what's going to happen is I'm going to let you sine of x means du is cosine of x dx. And what I really want to point out here is I could see that derivative right there of sine was right there. And so that's what we're going to need to be looking for. This is why we need to know the derivatives of each of these. So this transforms this into u to the 5th du, because the cosine x dx gets replaced with the du. And our goal is to recognize that derivative there. I know I just said that, but I'm going to say it a couple times today. So when we go back to that other screen, what I want you to see are all of these derivatives over here. And so we're going to be looking for a cosine, a sine, a secant squared, a cosecant squared, secant tangent, cosecant tangent, and so on. So that's going to kind of be our goal for the first part of this lesson today. All right, and this of course gives us 1/6 u to the 6th plus c, or 1/6 sine to the 6th x plus c. And that jumps us into our actual lesson. So here's our trigonometric manipulation. I'm going to start this here. And so far we have not integrated anything like cosine cubed x. But what we're going to do is we're going to use some Pythagorean rules. And I'm going to do this. I'm going to save off one of those cosines. And just like the previous problem, I'm going to recognize that cosine x dx is the derivative of sine x. Now I'm going to use a trigonometric manipulation, and specifically the Pythagorean identity, to rewrite the cosine squared x as 1 minus sine squared x. And what that's going to allow me to do is now that I have everything in terms of sine, I can just let u be sine, and there's my derivative. Like I said, I kind of saved it off for myself. So that u equals sine x, which means du cosine x dx. And you can see that right there. So we're going to intentionally try to induce that each time for many of these today. So this becomes 1 minus u squared du. And now it's just power rule, which is easy enough. And then we substitute back. For our final answer. So again, we used a Pythagorean identity. This is the sine squared x plus cosine squared x, and I just got cosine squared x by itself by subtracting the sine squared x. So not too bad. Now this is going to get pretty darn complicated here in just a minute. So for this one, what I'm going to do is I'm going to notice that I can save off a sine x, which is sort of the derivative of cosine x. So sine x, I'll say sine to the fourth x cosine squared x. And now I'm going to save off one of those because it was to the fifth here, sine x dx. And what I'm going to do now is I'm going to transform this, again, using a Pythagorean identity. This is going to be 1 minus cosine squared x squared. So that's like sine squared squared. So there's my sine squared squared. All right, so now I'm in a position to let u, to do a substitution, to let u be cosine x. And my du is right there. And that rewritten is going to be negative du is sine x dx. You can see it right there. Right there. So this becomes negative the integral of 1 minus u squared squared u squared du. So we're, again, deliberately saving off that derivative. I'm going to go ahead and FOIL that and then distribute the u squared. We are. And now, once again, it's just power rule. I could go distribute that -1. I'll do that all at the end. And that gives us a -1/3. Remember, u is cosine. Actually, all the signs are going to change because I distributed the negative. So minus 1/7 cosine 7th x, and don't forget, of course, plus c. So you can see that the algebra is getting a little more intense. For this next one, we're going to use one of those half angle rules. If you didn't get a chance to write that down or whatever, it's going to look like this. I'll use a different color. Let's use green. So it's going to be sine squared x equals 1/2 1 minus cosine of 2x. And you can see in this case, we have a definite interval, which is fine. But notice I can easily integrate that. That is no problem. But the sine squared, we've not done something like that before. Please note this is also a definite interval. So this is going to become, I'm going to pull that 1/2 out in front. 0 to pi 1 minus cosine of 2x. Please keep in mind that I'm going to get an extra 1/2 when I integrate that. That's a Calc 1 thing. Hopefully you've gone through that. So this gives us 1/2 x from 0 to pi minus 1/4. So that's the 1/2 here times the 1/2 that you get from integrating that. From 0 to pi. The zeros both go to 0 in both of these cases. So this gives me pi over 2 minus 0 minus 1/4. And this gives us sine of 2 pi, which is 0, minus sine of 0, which is also 0. So this whole part here goes to 0, which is very nice. And that gives us a final answer of just pi over 2. So this is a different way to manipulate it. We didn't save off a derivative in this case. All right, now we're going to do a variation on this exact same one here for our next example. Let's switch over. So sine to the 4th, once again, I'm going to use that trick, what I did before. I'll actually write it out this time. This is sine squared squared. Please note there are 2 ways to manipulate sine squared x. One of them is with the Pythagorean identity, and the other one is with the half angle identity. We're going to use that one here first. So this is, and I'll just rewrite it. So I did the previous thing in the other problem. But what's going to happen is instead of doing 1 minus cosine squared x, that's not going to help me in this case. I'm going to use the half angle identity. Okay. So I'm squaring this whole thing, which means I'm going to end up with a 1/4 out in front because of that 1/2. So 1/2 squared, I just pull it out in front. And now I'm going to square this here. So we're there. Now, I'm going to have to do that half angle identity again on this here. So I'm going to start integrating these very carefully. So this gives me 1/4 x minus 1/2, because 2 times 1/4 is 1/2. Plus I get an extra 1/2 there. Plus, not equals, plus. Now, I'm going to distribute this 1/4, and I'm going to do this half angle identity again, this here again. So I'm going to get an extra 1/2 times the 1/4. That gives me the 1/8. 1/8. And that is going to be 1 plus cosine of 4x. This is all plus c. This is the integral. So we've integrated that dx. And we're going to use the constant notation here, meaning we're going to get a different plus c when we integrate again. So this gives me 1/4 x minus 1/4 sine of 2x plus 1/8 x. So I can combine those up here in just a minute. And then that's going to be plus, now I get an extra 1/4 out of that. So that gives me 1/32 sine 4x plus c. All right, so that's going to give us, that's 2/8 plus 1/8 is 3/8, so 3/8 x minus 1/4 sine of 2x plus 1/32 sine 4th x plus c. That one is intense. You have to be really careful with that algebra there. All right, now we're to tangent and secant. And if we look back at our derivatives, we can see that I can rewrite this as the integral of tangent to the 6th secant squared x times secant squared x dx. I'm going to recognize right away that that is the derivative of tangent, secant squared. Now what I want to do is I'm going to use the trig manipulation, and I'm going to rewrite secant squared x as one plus tangent squared x. So you can look back in your Pythagorean piece there, and then here's our times secant squared x dx. So now I can let u, push this down a little bit, I'm going to let u equal tangent x times du secant squared x dx, and you can see that right there. So that's going to give us the integral of u to the 6th times 1 plus u squared du. And now we've completely transformed in terms of u, and I'm going to distribute that u to the 6th power. And now it's just polynomials, no problem. Giving us 1/7, and remember u up here is tangent. 1/7 x plus c. That is looking good. All right. This next one is actually very similar. So I'm going to work it out now, but I would recommend maybe that based on the previous example that we just did, maybe you try this one by pausing the recording and seeing if you can do it. And here we go. So I saved off that secant squared again. And I'm going to let, oh, I still need to change the secant squared using my Pythagorean identity. And again, there's my derivative. So if we let u equal to tangent x, du is going to be secant squared x dx. And there we are. Right there. All right, which transforms this into the integral of u squared times 1 plus u squared du. Using the distributive property. Now we have a nice power rule. No problem. And you're probably starting to see patterns develop, and they definitely are there. I'm not going to get into the patterns. I'd rather you understand why the patterns work, more so than memorizing the pattern themselves. The best way to learn a pattern is to do like 100 problems similar to it to understand why the pattern develops. All right, so we're on to the next page. A few more things, keep an eye on. So now we have this here, and I'm going to notice that I can save off a secant and a tangent. And what I'm going to do is I'm going to, and by the way, this is the derivative of secant. So I want to turn everything in terms of secant. So I'm going to take that tangent to the 4th x, and I'm going to rewrite it using a trig manipulation as the integral of secant squared x minus 1. I mentioned that at the beginning, that we can manipulate that rule a little bit, times secant to the 6th x, then times our derivative, secant x tangent x dx. And what I can do, now that I have everything in terms of secant, I can let u equal secant x, and du becomes secant x tangent x dx. And if you want to put the tangent first, it doesn't matter. It's the same thing. And there we have the derivative right there. So this becomes the integral of u squared minus 1 times u to the 6th du. So you're kind of getting a flavor for why we're calling it manipulation. That's what it is. I'm going to go ahead and distribute that u to the 6th. And now we have power rule, which we like. It's very easy to do. And now u, if you recall, is secant. We have it. And once again, and you'll note that when I pull out a tangent and a secant, it makes them even. Same thing's going to happen here. Here's another opportunity for you maybe to pause the video to see if you can apply what you just learned from the previous example 7 and apply that here. I'm going to continue, however. I'm going to once again save off a secant and a tangent. This is going to be tangent to the 4th x secant squared x times secant x tangent x dx. And I can see right away that I can transform the tangent into secant very easily because it has even exponents. So this is going to be rewritten as integral of secant squared, secant squared x minus 1 squared, because tangent to the fourth is tangent squared squared, so there's a squared times secant squared x times secant x tangent x dx. Now we have everything in terms of secant, so once again I can let u equals secant x, which means du is secant x tangent x dx. And once again, there we are. All right, so this becomes, actually let's squeeze that in there, the integral of u squared minus 1 squared times u squared du. So I'm going to FOIL that and then distribute the u squared. And now I'm going to distribute that u squared. And very nicely, we can, again, use the power rule, which is always nice. And then we just have to transform it back in terms of secant. So you can see this one's very much like the previous example. All right, on to example 9. Find the integral of tangent of x. So of all the things we've been doing, we haven't found the integral of tangent of x. Well, we are going to recall that tangent is sine x over cosine x dx. And I'm actually going to do a substitution. And I'm going to let u equal cosine x. Du is going to be negative sine x dx. And you can see we have our derivative there with an extra negative, which will come into play here in just a moment. So this becomes negative integral of 1 over u du. That's nice. All right, and by the way, you could find the integral of cotangent doing almost exactly the same thing, but everything's switched. This becomes negative ln, the absolute value of u plus c. And u, once again, is cosine. Now, you can leave it like this. This is not wrong to do. But if you remember with exponent rules, that -1 in front is actually the exponent for cosine x. Now, I want to make it clear. It's not, doesn't make it the inverse. Inverse cosine is different than cosine x to the negative first power. So most people write this formula like this. They actually flip. They do 1 over cosine, which is secant x plus c. Most books write it this way. I have seen some books write it like this. You'll have to see what your teacher says. I'm guessing they don't care. All right. And once again, I would challenge you to do cotangent to see what you get. With cotangent, you won't get that extra negative in there. So next up, is tangent to the third. But before we do that, we have a couple of rules we got to keep an eye on. So the inverse of secant, the integral of secant becomes the natural log, absolute value of secant x plus tangent x plus c. And the integral of cosecant becomes ln of absolute value of cosecant x minus cotangent x plus c. I'm not going to derive them for you in this video, but your teacher should be able to do that. It's not particularly difficult. It's just some genius came up with a wacky way of doing that. So we're going to need these integrals here in just a minute to do these last two. All right. So tangent cubed. Tangent cubed, I'm going to rewrite is tangent squared x times tangent x dx. Now, tangent x dx is not a derivative of anything, but what I'm going to do is I'm going to, once again, use my manipulation here to rewrite tangent squared x as secant squared x minus 1 times tangent x dx. And what we're going to do is I'm going to distribute that tangent x minus tangent x. And you'll note the previous example, example 9, was the integral of tangent of x. Now I'm going to do a substitution, but before I do that, I'm going to break this up into two separate integrals. Which we're allowed to do, it's a linear operator. And so I'm going to notice in this one, the derivative of tangent is right there, secant squared dx. This one we already proved. That was example 9. So I'm just going to straight up write that answer down. Before I do that, I'm going to do a substitution here. I'm going to let, and now I'm only going to do a substitution for this first integral. The second one is an independent integral, which I now have the solution to. So this u that I'm doing right now, let u equal tangent x, means du is secant squared x dx. And I want to point out that that is right there. So for the first integral, this becomes the integral of u du minus, and we now know that this is the natural log of the absolute value of secant x. We just proved that a few minutes ago. So this becomes 1/2 u squared minus absolute value of secant x plus c, which is 1/2, remember u is tangent, there we are with that. All right, number 11 is our last one for now. And I want to point out, this one gets very, very messy. Secant cubed. You saw tangent cubed, example 10. Example 11, we're going to use several different techniques of integration. So far, we know substitution. We also know integration by parts. That was section 7.1. And now we know trigonometric manipulation. We will use all of those as we're doing this. So I'm going to first start out by rewriting. This is the integral of secant x times secant squared x dx. And I'm actually going to do by parts. So, this is here. So by parts, we're going to let u equal secant x, dv is secant squared x dx means du is secant x tangent x dx, and then v is tangent x. So let's put it all together and see what we get. So if you remember, it's u times v, that's secant tangent, minus the integral of v du, of v, which is tangent, times here's du. So notice I'm going to get tangent squared here. All right, and remember, all this is equal to secant cubed. Well, what I'm going to do now is I'm going to transform tangent squared x into secant squared minus 1. So secant x tangent x minus the integral secant x times secant squared x minus 1 dx. And I'm going to distribute that and then break up the two integrals into two separate integrals. So we're saying the integral of secant cubed x equals secant x tangent x minus secant cubed, the integral of secant cubed x dx plus the integral of secant x dx. Now, I distributed the negative secant to here, and negative becomes plus. Now I'm going to note that what I can do is I can notice this is integral secant cubed. I'm going to actually add that to both sides. Ooh, forgot my dx there. Dx. And that is going to give me 2, the integral of secant cubed x dx equals secant x tangent x plus, now the integral of secant we just did up here. I didn't derive it for you, but so, oh, too far. There we go. So that's going to be ln, absolute value, of secant x plus tangent x plus c. And I'm going to use that plus c here. I'm going to divide everything through by 2. And so c, a constant divided by 2 is still a constant. So we end up with secant cubed x dx equals 1/2 secant x tangent x plus 1/2 natural log absolute value secant x plus tangent x plus, I'm just going to put plus c. And here is this crazy long answer. By the way, once you learn how to do this, you can also learn how to, or you can apply the same rules to find cosecant cubed x. Hope that helped.